Yeah, we were supposed to watch a video and answer questions with him one time. We just watched the game.
3.9. Let's go. We talked about before how you can separate mixtures. Filtration is used when you have a solid within a liquid, but if you have just a liquid mixture, then you can't use filtration. So we have some other ways to separate liquids. And the way that we use these is we take advantage of the differences in the intermolecular attractions of the components in the solution. So one important way is distillation, which depends on the differences in volatility of the components. So if it's volatile or not means how readily the substances will become a gas. So if it's more volatile, it's more likely to become a vapor or a gas. The most volatile component of the solution will vaporize at the lower temperature, and then a vapor is passed through a cool tube called a condenser, where it condenses back into a liquid state. So the one that I have is not this elaborate, but it basically does the same thing, where over here with the burner, you're heating up like water, and then the vapors will get trapped because everything's enclosed. It will get trapped and it will run through this tube. And then as you go through this tube, around it, there is open space where you will pipe in cool water, and so that it's completely surrounded by cool water. And so then the vapor will eventually condense or turn back into a liquid, and then it will be collected as it comes back out. So mine, it boils the water in the reservoir, and it goes up and over, and then it comes out into the front end, just the distillate, which is the pure water, invariably. The liquid component with a weaker intermolecular force will vaporize first. If the components are too similar, or if the solution contains several volatile substances, one-step distillation will not be an adequate separation method. You might have to do multiple steps. But this is a quick thing that it's not quick. It takes a long time to do a lot of water, but I do utilize this a lot for us in this class. The other way to separate components of a solution is by chromatography. Chromatography is a general name applied to a series of methods that use a system with two phases, a mobile phase and a stationary phase. So this is one way that it could look, where we will have a piece of filter paper, and we'll put a dot, and then we measure how high the dot travels. You might have done chromatography for it like in junior high, or if you were on the forensics team for Science Olympiad. But it's a way for us to see separating mixtures. So some definitions: the stationary phase is sometimes a solid, and that's also known as the adsorbent. The mobile phase is either a liquid or a gas. And the separation process occurs because the components of the mixture have different affinities for the two phases and thus move through the system at different rates. So what happens is the liquid will travel, and then eventually it will get stuck to the paper, and theoretically each part of the solution will get stuck to the paper at a different height. And so then you can identify what they are from that. The stationary phase or absorbent is the paper itself when we do paper chromatography. This is what our lab is going to be about. After a mixture is placed at the bottom of the paper, it's then placed in a solvent, or also the solvent is called eluent. And then the eluent moves up the paper strip by capillary action. So as it travels up, as the solvent travels up, then it also pulls with it, hopefully, your solution. We're going to use dyes. So this is what it looks like at the start, where you'll put a dot. And you want to make sure that your solvent, so in this case it's just water as the solvent, you want to make sure that the solvent doesn't cover your spot, so they have just ink. And the reason for that is because the ink might float into the water instead of crawling up the page. So you want to make sure that there's a separation of the solvent to the color dot, and then the solvent will creep up the paper, and once it hits the color, then it will pull the color with it. Okay, and then when it's done, at the end, whatever dyes or whatever colors you see within there, then it will all be separated out. So they're showing that this black dot actually had all those colors mixed together to make it, sort of thing. And then after we see the separation, then we can calculate what's called an RF value. So chromatography works in the concept that compounds can be separated that are slightly solution in the eluent and will spend some time dissolved in the eluent and some of the time on the adsorbent. The polarity of the molecules to be separated and the polarity of the eluent are very important. So if you have a very polar eluent, then polar substances will dissolve in it, but if you have polar and nonpolar, then they won't. So the polarity pulls into how far up the page are the dots going to be traveling. So choosing the right polarity is critical because this determines the level of separation that will be achieved. Different samples will spend varying amounts of time interacting with the paper and the solvent. Through these different interactions, the samples will move different distances along the chromatography paper. So what we measure with chromatography is the RF value, or also known as rate of flow. So the rate of flow will tell us how attractive the solvent and the sample are. So if when you solve it, and I have the equation on your notes and it's on the next slide for the example, but it's a ratio of the distance of the sample and how much that travels versus the overall solvent. You should never have the solvent be below the last sample. The solvent should always be above the last sample, okay? But when you solve for it with this ratio, if the distance of the sample is equal to the solvent distance, then that means that there's no affinity whatsoever for the paper, and so it's not going to stick to the paper. There's this intermolecular attraction fight between the solvent and the paper, and eventually you want the paper to win the fight so that the color will stay on the paper. But if the paper is not strong enough, then it will continue to go with the solvent as high as it goes. If you ever got a 0 answer for RF, that just means that the sample is immobile and it won't travel with the solvent at all. So it's not like a polar and a polar substance. So we want to calculate the RF values for A, B, and C. Can anybody guess what M is?
The second letters in the sentence.
It's all three of them together. Yeah. So the A, B, and C have been mixed. So like M could stand for mixture. And it's one thing that you could do with chromatography is you could have a mixture and you could have each of the separate components of the mixture, and you could do like 2 dots on a piece of paper and let them travel up. We are only going to do 1 dot on a piece of paper because of time and space. But you might be able to, like maybe you have 2 different, like you have a purple mixture and you need to know which color of red and which color of blue do you actually have in the mixture. Like, have you ever heard of red dye 40? The dyes that we're going to use in our lab are food dyes. And so I have a couple different reds and I have a couple different blues and I have a couple different yellows. So maybe you would have to do the mixture versus the separate red and red, and you see where does the mixture's red dot stop and compared to where does the other dot stop. So that's one way you could use it. But this is just to practice solving for RF, okay? So what's nice about this one is it gives you a guesstimate of measuring, so you don't actually have to have a ruler yourself right now. But the bottom number is going to be the same every time because the solvent distance is the same every time. Where do you think the solvent distance is?
4.8.
Like, yes, this line right here is the solvent line. So, yep, we want to make sure, we want to estimate our last digit. So 4.8 sounds great to me. So our solvent distance is going to be 4.8 centimeters. So in the denominator, it'll always be 4.8. Okay? Then we need to find the distance for each of the different samples. Now, for this one, let's just go to the top of the dot. We'll talk about tomorrow what to do if you have a really big dot. But let's just go to the tops of the dots. So what do you think A should be labeled as? 0.9?
0.8.
Well, we can only estimate one decimal place based on our
0.8. 1.
0.8 or 0.9. I don't care what you use. Okay. Then what about for B? 4.4? 4.3? I heard of 4.2, 4.4, so 4.3 is in the middle. If you want to use your number that you decided, that's fine. And then B? 1.8? I mean C. Did I say B?
My C went over the 2. I'd say mine's like 2.2.
Do you want to say 2.0?
No, it's definitely not.
I would say like 1.9. Mine's way over.
I don't know.
Mine's way under.
Okay, whatever. We're going to do 1.9.
Ugh.
So,
I can't erase with this pen. This L.
yeah. All right, so one person do A, one person do B, one person do C. Tell me what the RFs are. For C? Thanks.
B is 0.895833.
Does this have any units?
No, it's just a ratio, so there are no units. And what is that rounded to two significant figures?
0.90.
Thank you. Okay. Now the RF values are not going to add to 1. They're all their own unique number. They don't relate to anything else. They're just all their own number. And so the ratio value tells you how attractive is it to the paper versus how attractive is it to the solvent. So if the RF value is very big, do you think it's more attractive to the solvent or more attractive to the paper? It's more attractive to the solvent. So if you have a larger RF value, it's more attractive to the solvent, and that's what allows it to travel higher. But if it has a very small RF value, then that means it's more attractive to the paper, and so the paper holds it at a lower spot compared to the rest of the solvent. Okay? The math should be pretty simple and straightforward, just the concept behind it is a little difficult for some people. 0.40? Oh, okay. Okay. Yeah, that's fine. All right, so we are going to be doing this with our lab tomorrow after we do our chromatography. There's another type of chromatography. It's called TLC. It's called thin layer chromatography. That's done exactly as it says. Instead of having a piece of paper, you have a thin layer of silica gel or alumina that's coated on a piece of glass, and then it's very hard to see, I feel like, in this, but they're pretty big plates, and then you would what you have to do this for is you have very non-volatile substances, and so the testing chamber actually has to get a lid on it so that the vapors can just cover the entire plate. And another reason why you would use a TLC plate versus a piece of paper for chromatography would be that TLC plates are treated to show sample spots under UV light. So I have this picture here of a chromatography on a plate where they're shining a UV light on it so you can see the different spots there. So maybe your mixture is not visible, but it will be visible under the UV light instead of under normal lights, kind of thing. And so that would be one way to do that. We do not use the chromatography with the TLC plates because ours works with paper and it's cheaper to do it on paper. So that's what we're going to do in here. Okay, so that's it for 3.9.